Another example about normal and shear strain. Okay, here we have a figure shown here. Just start from a rectangular shape and then it deformed to the dashed line indicated shape. Then we have given the delta AX, BY, CX, DX, DY, etc. And the original length LA is 400 millimeter. Okay, then we determine the normal strain in X direction at corner A and the normal strain in Y direction at corner A and the shear strain at corner A. In this example, you can see that this is actually much closer to a practical problem because the original size is very large, it's 400 millimeter, and the true dimension, the true deformations are very small, only 0.some millimeters. So because of these small deformations, we can do some approximations. You will see that we will do some approximations in the calculation process. Okay, so first step, let's look at how to find the normal strain in X direction at point A. Okay, the step A, normal strain at point A along X direction. Okay, so here it would be this, we're finding epsilon X at point A. Right, so we just need to find the deformation at the point A along X direction, right, over the original length, that is LA. Okay, LA or LAD, right? LAD, it just equals LA, that's 400 millimeter. Okay, since we already know LAD, we just need to find delta AX, okay, the deformation at point A along X direction. Right, based on the values that have been given, so you can see that the side AD here is elongated at the D side by delta DX, but it shrinks at the A side by delta AX. So what is the overall deformation or change in length? The delta AX can be calculated as delta dx minus delta AX, right? So on one side it becomes larger, and the other side it becomes smaller. Okay, so from here we can get the overall deformation along X direction. This is just along X direction, not the deformation, the true deformation of AD. Right? So we're not using A prime D prime minus AD to calculate the deformation of the side AD. We're calculating the deformation along X direction at point A. Okay, so this will be this delta dx minus delta AX. Okay, the first value is 0.7, the second one is 0.3. So we get 0.4 millimeter. So the delta X will be 0.4 over 400. Okay, so that is 0.001 strain or 1000 microstrain. Then step B, the normal strain in Y direction at point A. Again, we're not using A prime, B prime minus AB to find the deformation. We're just looking for the deformation along Y direction. Okay, so this would be epsilon Y, delta A along the deformation at point A along Y direction over L AB. Right, this is also LA, right? So we just need to find the delta AY. So what is delta AY in this case? The deformation along Y direction. Okay, you can see that along Y direction the deformation is just delta by, but negative, right? Since it's compressing downward, so this is negative delta by, or negative 0.25 millimeter. Right, so the epsilon y would be negative 0.25 over 400. So this would be negative 0.000625 strain, or negative 625 microstrain. Then the last step, we're looking for the shear strain tau xy. This is gamma xy, right? At corner A. So at corner A, here the original angle between x and y is just pi over 2, right? Alpha equals pi over 2. And after deformation is the angle is here. Right, the angle is here. This is our beta to find. But how can we find this beta? It's a very large angle. Right? This is not easy. But we can get the beta from pi minus two smaller angles. Right, this is the first one. Let's call it gamma 1. And here, let's call it gamma 2. So here, in the step C, we're just looking for gamma xy, and we're calculating it from alpha minus beta, and alpha is what? It's pi over 2, right? Minus beta, and we're looking for beta, right? So here, as we have realized that the beta can be calculated from pi minus gamma 1 minus gamma 2, right? So is that easy to find gamma 1? Gamma 1 can be found in this small triangle. Let's use another color to denote it. The green colored thing here. Right, in this green small triangle, okay, we have now this side length is delta dy, and you just need to find another size, right, the overall size. Okay, the gamma 1 can be found here, like we don't know it yet, but tangent gamma 1 equals delta dy over the length. Over that length will be LAD plus dy plus delta dy plus delta dy minus delta A. Sorry, this is delta dx, right, minus delta AX. We can see that this part is very small, right? This part is very, very small, so we can ignore it. Basically, this one approximately equals delta dy is what? 0.1. Right, it's 0.1 over LAD is just LA 400. Okay, plus delta dx minus delta AX, right, will be just a 0.4. Okay, it will not affect the results significantly. So we can just ignore them, do this approximation, and here it would be 0.00025 radian. Okay, this is a definitely small enough angle, so we can say that gamma 1 equals tangent gamma 1 equals 0.00025 radian. Okay, so then how about the other one, the gamma 2? Is that easy to find gamma 2? Gamma 2 is a larger angle, so we kind of do approximations. But here we have another one. Here we have a gamma 3. Let's call it a gamma 3. Okay, let's call this angle a gamma 3. So the gamma 2 can be calculated from pi over 2 minus gamma 3. Right? So gamma 3 can be solved from the blue colored triangle. Right? From the blue colored triangle here. Right, so tangent gamma 3 tangent gamma 3 can be calculated as delta AY, delta AX, right? Delta AX over LAB minus delta BY. Again, this is a very small number as compared to the original size, so we can ignore it. So approximately, this would be 0.3 over 400, and that is 0.00075 radian. Again, this is a very small number, so we can assume that gamma 3 is 0.00075 radian. Now you can see that the gamma xy at point A equals what? Equals here pi over 2 minus a beta, and the beta equals what? According to this one, pi minus gamma 1 minus gamma 2, and gamma 2 equals what? Equals pi over 2 minus gamma 3. Right? So this one equals gamma 1 minus gamma 3 will be negative 0.0005 radian, or negative 500 microradian. Okay, negative means that this angle is larger than pi over 2.